Hi, welcome to another lecture on Calculus 2. Today we are going to talk about comparison of series. This is going to be a method of finding out convergence or divergence of a series based on the same information from another series. Let's go ahead, take a look at the list of topics for today. We have three topics to talk about. One is called direct comparison test. The other one is called limit comparison test. And the last, we are going to talk about leading term analysis for finding a comparison series. Before we get into the mathematical detail here, let me take a slight detour to explain why is it that we are spending so much time on this topic. A question I promised we'll talk about a few lectures ago as to the uses of this topic. Mathematically speaking, of course, these topics are well liked in mathematical area, but most of students who are taking calculus are students in sciences or engineering, and so it's a good idea to go ahead and explain where this effort is going to be used. So to explain that, let me just bring up a topic from high school. So in high school we start studying algebra. We learn about polynomials, x squared, x cubed, and so on. And much of the beginning algebra 1 and 2 revolves around the description of these type of functions. Then we come to pre-calculus and calculus 1, and then we are introduced to new functions such as sine, cosine, exponential, and so on. So our horizon expands when we have all these new functions to study. A natural question comes up. Are these functions like those high school functions? Is sine and cosine, is it like those polynomials we had in high school? In polynomials we had like x plus x squared plus x cubed and so on. Are these two in the same family, or is it a different family? So let's go ahead, take a look at a basic function you come across in your pre-calculus or your calculus class. Trig functions, you study them extensively. Sine of x, perhaps the first one you come across. So the question comes up, what's the relationship between this and all those polynomials we studied in algebra 1 and algebra 2? So if we go look at this thing, well, this doesn't look like any of those polynomials we studied, but if we limit ourselves perhaps to one location, we might have a better luck. If I look at around the origin, I see that this function looks like it's taking off at 45 degrees. So it kind of looks like a very basic function we study in calculus in high school. Y equal to x. This blue and the red are close to each other near the origin. You see the gap between the two of them quite small here. Of course, as we move far away, there's a huge gap. So if I just zoom in, yes, they look like each other. But if I zoom out, well, we see big difference between these two. So how can we bring them close to each other? Well, I can bring in more terms of a polynomial, see what happens. So I say, well, what if I add x squared? Well, we notice that x squared makes my picture lopsided. The red one, sine of x, had a so-called symmetry with respect to origin. If you remember from your algebra or pre-calculus, we call that an odd function. If you change x to minus x, sine also changes from plus to minus. So that gives us an idea to just use the odd powers. They have the same property as sine of x. So I say, okay, x squared is not a good candidate. Let's add x cubed. So I add x cubed. Well, it looks like I made my picture worse than it was. This blue one was coming close to the red, a lot better than this. Well, then that gives me an idea. Let's make a correction. Perhaps if I subtract, well, I subtracted and the green one is acting better than before, but still it looks like blue is a better bet than the green. So I said maybe I'm subtracting too much. If I subtract half, maybe it's better. If I subtract a third of this, it got a little bit better. Well, the question comes up, what's a magic number? This x cubed, what should I divide it by so that I get the best match? So 5, it got better. 6, it got much better. Well, it all going to depend on your point of view of what number to use here. We are going to come back to this issue later on. It turns out from our point of view that 6 is a magic number that brings this green curve as close as possible to the red one. We can of course keep going, like divide by 7. By now you see the green extending above the red, and so on. You know, the gap, there's another gap to talk about. So for now, let's just divide by 6. So okay, we notice that the green curve is coming close to our sign, meaning x minus x cubed over 6 is a good approximation for sine of x in the vicinity of origin. Of course, if I go far away, the gap between the green and the red is again big. Try to cure this gap. Can I bring this green close to the red? So okay, now let's go ahead, take another stab at this thing. X minus x cubed divided by 6. Let's add another term. We agreed that even terms are not a good match here. We are going to go after odd ones, and playing around we are going to notice that x to the power of 5. Now again, we are overshooting by quite a bit. To improve it, we go ahead and divide it by some number. Again, we are going to see later on where do these magic numbers come from, and the magic number here happens to be 120. Okay, we are going to explain that later on, but right now the point is that this strong blue is coming closer to the red one, to sine of x, than either the green or the light blue one. So I am kind of making my polynomial come closer and closer to the sine. What do you think is going to be next attempt we are going to make here? So I copy what I have so far, divided by 6 plus x to the power of 5 divided by 120, and then, well, you can guess that if I subtract some terms, I might make this come even closer, and so what we are going to have is a sequence of odd powers of x, and next one is going to be of course 7, and by now we are, that's the black curve. You notice that is doing worse than the other ones, but if I divide it by the right number, I can bring it close, and the next number turns out to be 5040. Notice first that the black one, the new curve, is matching the sign very well all the way up to the first intersection here. This is a very good match for my sign, and later on it deviates. You might be curious as to what these numbers are, the magical numbers. These are factorial numbers. 3 factorial is 6, 5 factorial is 120, 7 factorial is 5040. We have seen this factorial in the case of sequences before, and now they show up, and they show up quite frequently in the sequel of topics that we are going to have. So what we see here, we see a sequence of functions. Every time I'm adding one more term to it. So this itself is a series. It's a series where a parameter x appears in it. So that opens the door to a whole set of questions. You remember we were trying to see how to express sine of x in terms of things we had seen in high school, and in high school we had seen these polynomials. We see that it's possible to make a polynomial to act like this function that we have, the sine x. But at a price. What's the price? The price is that we keep adding more and more terms to close the gap between the two of them. So in fact, we need infinitely many terms here to actually reproduce that sine of x. So what we have here is a series that duplicates a function that didn't look like a polynomial to begin with. So at this point, we are motivated to understand how do series behave. We are faced with the issue of infinity here. We have to add infinitely many terms. We have to make sense of that. And all the topics we are talking about here come in naturally at that stage. Again, this is something that we are going to study later on under the topic of the Taylor series theorem and so on. But I just wanted to give you a preview of what is coming and what's the reason we are studying all these things that we do. So by the end of this chapter, you're going to see perhaps a dozen of these tests and such. And you might be wondering, well, why are we studying all of these things? So I try to give an answer to that. Okay, let's go ahead and explain this. Direct comparison, very intuitive idea. If I have two sequences, AN and BN, out of which I'm making two series, and they happen to be positive, and one of them dominates the other one, meaning like BN is larger than AN. Then, if the larger one converges, if the sum of BN's converge, we can conclude the smaller one also converge. Essentially, the larger one is preventing from the smaller one from running to infinity. If you know this converges, the smaller one definitely diverges. On the other hand, if we know the smaller one diverges, then we can conclude that the bigger one is going to diverge as well. So that is so-called direct comparison test. Sometimes the comparison is not easy to achieve. We have some other method a bit more advanced, but very similar to this. It's called the limit comparison test. In this case, we have two sequences. Terms of both of them are positive, and it is assumed that the ratio of one to the other has a limit. That limit exists, is positive, and it's a finite number. In that case, we can say that these two series behave like each other, meaning either they both are going to converge or they both are going to diverge. So for example, if one of them almost twice as big as the other one, that means this limit is 2. Well, it stands to reason that if one of them converges, well, the other one will converge as well. If one diverge, the other one will diverge as well. We are going to postpone the proofs to another lecture, and what we are going to do in this lecture is just to apply this thing, assuming that the idea looks intuitive to you. And the third one would be, well, if we have given a series, how do we go find the second one for the purpose of these kind of tests? So let's get started by doing some example in this case. So let's get started. Use comparison test to show that the following series converges. So in this problem, we are given a hint that it actually converges, and what we want to do is we want to use the comparison test for establishing that it actually does converge. Well, we come and look at this thing, and now we need to apply some ideas as to finding another series that we already know that it converges, that's going to help us to establish that this one is going to converge. So we say the leading term here is 4 to the power of n. If I eliminate this 5 here, I get a series that is bigger than this. That is, notice that 1 over 5 plus 4 to the power of n, this is smaller than 1 over just 4 to the power of n. Why? Because, well, if you make a denominator bigger, your fraction gets smaller. So this is definitely less than that. Now we ask the question like this: do I know the series built on this term converges or not? If I have the sum of 1 over 4 to the power of n, can I arrive at a conclusion as to if it converges or diverges? And if it does converge, what does it converge to? Well, we notice immediately that this is a geometric series. The geometric series, you remember, let me remind you, if you have sum of a r to the power of n and you are adding this thing up say from 0 to infinity, this thing converges to a over 1 minus r, provided that your multiple term is less than 1. In general, if you had a geometric series that converges, the sum of a geometric series is equal to, if you want to remember it easily, is the first term over 1 minus the multiplier or the ratio. So in this case, our first term, here we are starting at 1, our first term is 1/4. Multiplier, every time we are multiplying by 1/4 again. Let me write this so that I make sure everybody follows the discussion. At n equal to 1, we are starting with 1/4. At n equal to 2, I have 16. N equal to 3, I have 64, and so on. If I want to add up this geometric series, how does it go? The first term is 1/4. 1 minus, now the ratio of each term to the previous, like 1/16 to 1/4 is 1/4. Or if you wish, 1 over 64 to 1/16, that is 1/4. The ratio of any two consecutive is 1/4. So it's going to be 1/4 over 3/4, and that is 1/3. So the series built on this converges, moreover it converges to 1/3. Therefore, this series whose terms are smaller than this, first of all, it's going to converge, and secondly, it's going to converge to some number less than 1/3. So use the comparison test. We say, first of all, we have to show an inequality of terms of this series versus another one. Second, we have to show that we know the convergence or divergence of this, and therefore we can establish that the series 1 over 5 plus 4 to the n, first of all, it converges, and then we know that the sum is less than 1/3. So that is how to establish convergence based on this idea. Here's another example. Suppose I ask, find the convergence or divergence of 1 over radical n minus 1, and I'm adding from 2 to infinity. Before we go any further, you might be asking why are we starting from 2? Well, because if you put n equal to 1, you're dividing by 0, and that doesn't make sense. So we might always start a series at some arbitrary location, and that does not influence the convergence or divergence. We can always set aside the first few terms for whatever reason we have in mind. So here the question again is, I want to establish the convergence or divergence of this thing. First of all, I have to come up with an idea which way do I think it actually going to go. Is it going to converge or diverge? So I do a leading term analysis. I say, okay, when n gets to be large, minus 1 is not a significant term here. The dominating expression is 1 over radical n, and I know from P series that this is a divergent series if I have sum of 1 over radical n, or the sum of 1 over n to power of 1/2, regardless of where you start it at 1 or at 2 or something, this thing diverges. Now you can give a variety of reasons for this thing. You can say this is a by P series test, because the exponent is less than 1. We know that when the exponent is less than 1, it is an indication that it will diverge. Or you can do an integral test if you wish. Directly you can do an integral test. That is, if you have 1 over radical x and you try to integrate that from somewhere to infinity, that one also diverges. Okay, so that gives us a hint or a motivation to go after establishing that this thing is going to diverge. So our first decision is which way is it that we think is going to go. Is it going to diverge or converge? So we are inclining toward establishing that this thing is going to diverge. Now, according to this comparison test, if I want to show that something diverges, I want to show that something that is smaller than that even diverges. So that's one approach we can take. Say 1 over radical n is less than 1 over radical n minus 1. For n's 2 or larger, I can have that this term for, so again we are staying away from division by 0 and such. So staying at n larger than 2, this is a true statement. Why is that so? Well, if you subtract something from denominator of a fraction, then the fraction gets bigger. Is that right? This denominator is smaller than this denominator, so the fraction is bigger. And I know this smaller sequence leads to a series that series is going to diverge. If I go ahead and add the smaller one, I know this one diverges to infinity. As a result, I can say the series whose terms are bigger than this, okay, the terms here are bigger than the terms here, therefore I know that this one is going to also this is going to also diverge. Okay, now establishing this inequality sometimes can be a bit trickier than what we have here, but the first few examples we looked at are rather straightforward. Okay, let's go ahead, take a look at the second type of comparison test we had, and that was the case of the limit comparison test. Again, the issue is establishing that inequality. Inequality can be consuming more time from us than everything else in this type of problems. So if we want to have a quick verdict as to if a series is converging or diverging, a very quick approach is the limit comparison test, because we don't have to fiddle around with the inequality all that much. So here is an example. Suppose the question is find convergence or divergence of sum of 1 over say 5n squared plus 7n plus say 11 and starting from 1 to infinity. We want to go after a series that we know if it converges or diverges, and compare with this and come up with a quick conclusion. So again, we do a leading term analysis here. Leading term meaning I look at this thing, so what is the most significant term here? Most significant term is this n squared. This is when n goes to infinity. The biggest drive here is this term n squared. N is getting to infinity, but that's much smaller than this, and this 11 or whatever number I have here is a constant number while the other one is going to infinity. So this leads us to the idea of, let's look at as a comparison, let's go ahead and look at sum of 1 over you can even do away with the 5 and make it as clean as you want, sum of 1 over n squared. So we come up with what to compare it with. Sometimes the problem tells us, most often it doesn't. Now 1 over n squared, we know from integral test or the p-series test that this one converges. Okay, from the p-series or the integral test, we know immediately that this thing converges. So how do I use a limit comparison test? I take a ratio of these two. So I take a ratio 1 over n squared over 1 over 5n squared plus 7n plus 11. Cross multiply, this becomes 5n squared plus 7n plus 11 over n squared. Simplify this thing, becomes 5 plus 7 over n plus 11 over n squared. Okay, now we ask ourselves, as n goes to infinity, what happens to this? As n goes to infinity, there is a limit. That limit is positive and is not infinity, is not 0 either. It is a definite number between 0 and infinity, and that is what this theorem requires. So if you have two sequences, the ratio of them has a limit that first of all, limit does exist, second it's positive, and third it's finite. Then the two series that are built based on these two, either both of them converge or both of them diverge. So here we are essentially saying that this series is comparable to that. The reason for this is that the limit of the ratio of the two terms is a number between 0 and 1. That means if one of them converges, so will the other one. I know this one converges because of the p-series test or because of the integral test. This exponent is larger than 1, so this one converges. As a result, I know that this one will converge as well. Okay, so you notice that we came to a conclusion very quickly here. We didn't have to do any inequality work, and the approach is quite quick. Of course, that means that if we are estimating based on this, our work is going to be less precise, but as far as establishing convergence, we can establish it quickly. Okay, So you'll have a few more exercises on this, and we're gonna have a separate lecture on the proof of these theorem. That's gonna be for students who are headed toward mathematics, who might want to know the reason for some of these statements. Okay, so until next lecture, good luck and God bless.